This project is an update to the known new craters on Mars that are out there. These have been kind of partially published in a number of papers, but this is somewhat motivated because people keep asking me for my list, and it's been kind of an unorganized disaster for a long time, frankly. But there's a lot of really good work that can be done having the full list and having those statistics. So so we're getting it out there, and thanks in part to an SSW grant, acknowledged there. And I also wanted to thank some of my co-authors, Annabelle Gao, Dan Wexler, Tanya Neidhart, and Jonas Eschenfelder, who have done a large number of the measurements and categorization that you'll see presented here. So a little bit of history if you're not familiar with these new craters on Mars, that the way that they're found is with before and after images, where the before image does not have an impact and the after image does have an impact. So we can constrain their data formation that way. This was originally done with the Mars orbital camera on MGS. The paper came out in 2006 by Malin et al. And that was done with a concerted imaging campaign into areas of Mars, and they found 20 sites that were new that way. Nowadays, we largely use the context camera and the Mars Reconnaissance Orbiter to do this. We do use other data sets to compare to get the tightest date constraints on those formations, but CTX is really the workhorse for this, finding new craters. So this is an example where you can see the before and after image. It's not there, and then it is. So we know it's a new impact. And then we can follow up with the high-res camera and get a high-resolution, oops, just lost my screen. There we go, get a high-resolution image that allows us to do things like measure the diameters of these very small craters. Note the scale bar there is just 50 meters. So most of these craters are just a few to tens of meters in diameter. We can map out the precise locations in the cluster, and we can see the details of these kind of interesting albedo patterns around a lot of them. These are mostly dark blast zones caused by the impact. We don't always know the exact mechanism, but you'll note that it's many times larger than the crater itself, and that's what allows us to actually find the impacts in the lower resolution context images. So over the last decade or so, these new craters have revealed a lot of things about Mars. There have been a subset that actually excavated clean, shallow ice in the mid-latitudes. We've been able to measure the current cratering rate with them, look at their morphology. We've looked at the properties of clusters to get things like the impact angle and azimuth. Those blast zones, we've used that clearing of dust to kind of take advantage and look at the mineralogy beneath that dust layer. Gwen Bart has looked at the size of the halos around them and how that correlates with the crater diameter. We've looked at the fading of these blast zones over time with repeat high-res imaging, and this is fed into things like different models for atmospheric fragmentation by Hartman and others. We've actually used them to update the standard Hartman chronology, and that has been used by Margaret Landis and others to do things like estimate the ages of the polar layer deposits. So given all these cool things that we've done with the new craters, why do we really care about having more of them or cataloging more of them? Well, part of that, I think it's just we're all scientists and we're driven to see all the data and we want completeness. But there's a number of other more practical reasons. You know, if we keep looking for these, we have a longer temporal baseline, and that allows us just statistically to have a higher chance of catching more large impacts. And you'll see in the results that we are doing that. We get better statistics, especially of kind of more rare types of impacts and different kinds of features like light tone blast zones that you see here. We can extend our aerial coverage. So for example, those ice exposing impacts at the mid-latitudes, we know of a lot more in the southern hemisphere now than we did a decade ago. And we are able to better understand the observational biases in this data set. And finally, we have a larger set of well-constrained formation dates, which allows us to investigate short-term variability in the impact rate, for example. So just some preliminary statistics. This will all probably change because we're finding new ones every day, but to update you on where we are so far. Right now we have almost 1,100 known dated sites. About more than 800 of those have been completely kind of measured and mapped out and categorized as of, I guess that's just last week. A little more than half of them are clusters. This has been fairly consistent over time that we find a little bit more than half is clusters. And more than half of those clusters have been kind of mapped out in detail with the locations and diameters measured. The largest crater we found is almost 60 meters in diameter, which probably sounds really small to most of you, but it's really exciting to us because most of them are, you know, just a few meters in diameter. And that's this one you can see here in the purple outline. And the most populated cluster we found so far has 465 craters, which, you know, good job to the person who counted all those craters and measured them in their locations. So using this, this big catalog, we can start to look at a number of different things, and I'm just going to show some examples. This shows a little bit about how common different types of features are that we see and how that breaks down by single and cluster impacts. So for example, halos are this kind of quasi-circular, nebulous dark area around the impact site. And the occurrence of those seem to be fairly consistent. These are percentages here, fairly consistent between singles and clusters, and they are present at a lot of the impact sites. We also see these kind of extended straight rays coming directly from the impact site. These are also fairly consistent between singles and clusters and are probably our second most common type of feature. Some of the more rare features we see are these arcuate rays, like this one here that we think is probably has to do with the interaction of the impact blast and the surface in some way. We also see light-toned and dual-toned impact sites where we think it's probably has to do with the surface properties and the albedos of the surface materials that are moved around during impact. And again, those are fairly rare types of features, but now that we have this big data set, we can start to look at some good statistics of them. So as an example, we can look at how those dual-toned and light-toned blast zones vary over by latitude. I'll note at the high latitude, it's pretty small number of statistics, but in the middle latitudes, we're starting to build up some good numbers. And you can see that there's definitely a prevalence here of the light tone blast zones in the southern hemisphere. So that could be because there are just certain types of terrains that are more favorable to the formation of those types of features. But that's something we want to look into more. Another thing we can look at is how clusters kind of vary with elevation. So I started with kind of a naive hypothesis that maybe there would be more clusters at lower elevations because there's a longer atmospheric path length, there's more time for things to break up. When we actually looked at the percentage of sites that are clusters as a function of elevation, we didn't really see that. It's a much more complicated situation. Again, the very highest elevations are very small number statistics. That's the number of sites shown there. So we're not sure if we can trust those, but even in the elevations where we really have a good number of samples, there's kind of a much flatter distribution than I would have expected, and maybe some hints of structure there that we really don't understand yet. We could also try to look at dispersion or how spread out the cluster is as a function of elevation. And again, this is something where I thought lower elevations would probably have more dispersion because again, you have more time traveling through the atmosphere to spread out and more opportunities to kind of break up and have maybe successive breakups. We thought we saw that in our 2019 paper, which is the blue dots here, where the lower elevations, there's a lot of scatter here, obviously, but the lower elevations tended to have more dispersion. But now that we're making the measurements for all of the sites, you know, maybe that's not quite bearing out. We really have to look into that. Some of the higher elevation ones also have pretty high dispersion. So that's something we need to figure out. We can also look at the aerial extent of the locations of these sites. For comparison, this is the 248 sites that we knew of in 2013 that were published in that paper. And now we know of almost 1,100. And you can see that if I'm going to blink back and forth between them, you can see we're starting to fill in areas like in the Southern Hemisphere where we didn't have a lot before. But the kind of popular areas are really still popular. So we definitely are getting an aerial observational bias, and we think that that is due to differing surface properties over Mars. So this is a map of thermal inertia. If you've ever seen me talk about this before, I often plot it on a map of the dust cover index, but my co-author Sylvain Picu pointed out that the thermal inertia map is actually a much better predictor of where we're finding these new impacts. And that could be because the dust cover shows where there's dust, but it doesn't necessarily show the level of induration. So, so the thermal inertia is actually a better predictor of how much stuff is loose to move around when the impact happens. So that's, again, something we want to look at more. Michelle, I saw you pop up. Was there a ding or something?
Sorry, not yet. No.
Okay. There are some new results coming out from my co-author Colin Dundas about the ice exposing craters. This is confirming the presence of widespread clean subsurface ice at shallow depths in the middle latitudes. The lowest latitude is 39 north, and above 50, you really see these icy impacts at all longitudes. There are some longitudinal variations at lower latitudes that could be due to various differences in terrains. Thank you. And some of his results have also looked at the depth to which ice is exposed. So if you use a very simple relationship between the size of the crater and the depth to which it excavates, you can see that ice is being excavated at depths of 1 meter and even less at the high latitudes, and it gets a bit deeper down to a few meters at the lower latitudes. And we're seeing that in both the northern and the southern hemisphere. So not all the clusters are completely mapped out yet. So one thing we wanted to look at was whether using the size of the largest crater in the cluster could be used as a proxy for the size of the impact. That would be really useful as kind of a quick estimate for the size of the impact. And so something we looked at was kind of a correlation between the largest diameter in the cluster and the effective diameter. Of course, the effective diameter is always going to be larger because it includes all of the small ones, not just the largest. But you'll see that there's, again, a lot of scatter, but you'll see that the kind of best fit trend line there isn't too far off of a relationship that we could use. And when you look at it in terms of the percentage difference between the two of them, you'll see that there are some that are 50, 60% different, but the vast majority of them are 10, 20, 30%. So it's actually a pretty good estimate. And if we think about it in terms of the kind of standard root 2 bins that we all use in our size frequency distributions, this is just a bar chart showing how many are going to be in different bins if you use this as a proxy. And most of them are in the same, if not one bin over. In fact, 86% are in that, and only 14% are 2 bins different, and I think there's only one case where it's 3 bins. So we could use this as a proxy eventually if we don't map all of the clusters, or if we get new ones and we just don't have time. So speaking of size frequency distributions, I just want to show you the evolution of this over time. These are the originally Malin et al. Sites from 2006. You'll notice that I blanked out the y-axis because I'm not scaling this to area. I just want to show the shape of the distribution and the actual numbers that we're getting and how that's changed over time. So in 2013, we knew of 44 sites that we could put on this chart. And then in 2014, we were up to 110. And then the current data set, this only shows 436 of those sites, but eventually we're going to put them all in there. So a few things to note is that we're extending this out to larger diameters as well as smaller ones. And of course, the numbers are much higher, which is great. Our error bars are shrinking. And the rollover diameter, you'll see, actually hasn't changed, which I thought was encouraging because it points to that we're not necessarily missing a lot of small ones because we haven't imaged them. It does seem to be a true effect of the resolution of the data that we're using to find these. I looked at the slopes of the size frequency distribution because it can be a useful comparison across different bodies. We use them to differentiate sometimes primary and secondary populations. And more importantly, we can get it without scaling to the area, which in this case is a really complicated project because there's many different data sets being used to find these and they have different times between them. So we could just look at the shape of the distribution without caring where it lies on the y-axis exactly. That could still give us some interesting results. So the slope that we get for the differential SFD is 3.6, and you'll note that that's quite a bit steeper than when we had fewer reported in 2013. So this isn't the full data set yet. It's just the ones measured thus far, so there's more singles just because they're easier to measure. So once we get all of the data included in there, it'll be interesting to see if this holds up and what that might mean. So these data are also being used to look at atmospheric fragmentation processes. There was an LPSC abstract last year by Newland et al. That looked at several different types of fragmentation models, did some Monte Carlo modeling to predict what that would look like in terms of some statistics of the clusters that we've looked at. And the results here strongly support this multi-component fragment cloud model versus kind of more traditional successive fragmentation models. So as we measure more, that's actually been still bearing out to be true. The new ones are in red here. So eventually this catalog is going to include the locations of all of these new impacts, information about the observations that we use to do the measurements, constraining images and dates, diameters and effective diameters for clusters, but we want this catalog to be useful to the whole community. So one of the reasons I really wanted to talk to this group specifically about this was, we're open to suggestions about what would be useful for you all, because we have seen so many cool projects come out of these new craters, and I think having the whole catalog out there hopefully will be useful to everyone. So so stay tuned, that'll be coming out soon, and I'm open to questions. Thank you.
Thanks, Ingrid. Great. Looks like a very interesting database, and I know it's already helped to answer very many questions. And we have some more in the chat, so I'll let Stuart take over.
Yeah, there are several questions. First, again, apologies for pronunciation. Ankush, does any new crater show a signature of ice or water? I think you addressed that already.
Yeah, I can go back and show some examples, and I would refer you especially to Colin Dundas's work on this. He had a paper a couple years ago with an update, and there's another one coming out. So all of the white dots on this map of Mars show icy craters where it's exposed water ice, where the formation of the impact itself has exposed subsurface ice.
Okay. Next up is Alvaro Suarez. Morphologically, are all the craters circular, or do they have other shapes? And I guess besides the clusters.
Yeah, a lot of them are pretty irregular. These are small impacts, and they're often heavily influenced by the pre-existing topography. There's a good chance they've been pretty severely decelerated. We do think they're all still hypervelocity impacts, but probably at fairly low speeds. So again, I don't know if I have any examples of them here, but they are often irregular in shape, both in topography and in kind of plan view. So you can see in this is the biggest one. The rim is pretty irregular. It's got kind of a bench or concentric crater going on there. So yeah, they get a little complicated. Mm-hmm.
All right. Next up, I'm going to kill two questions with one. Paul Schenk notes on your size frequency distributions that the error bars these days look really, really small, and he was wondering if they were too small. And then there was another question by, I think, Fred Califf. Are there any thoughts about why the size frequency distribution slope has changed in the latest data set, the 436 sites, because that slope does look different?
Yeah.
Is there a bias towards sampling certain diameters?
Yeah, okay. So the first one, I should say these are the standard error bars that Crater Stats puts on there, which a number of people think are too small. You know, the really long error bars, I mean, there's only one in that site. And you know, the rest of them are fairly well populated though. So, you know, take that with a grain of salt. And then I think the second question was about why the slope might be appearing to be steeper. I don't know the answer to that. That's something we're hoping to look into. It's possible that as we have improved our statistics, we're just finding more small ones. But there's also, obviously, there's some impacts of the different observational biases that could be size dependent. So for example, when we looked at the fading rates of these blast zones, we found that larger blast zones tend to fade, or the blast zones around larger craters tend to fade more slowly. So that does mean that perhaps larger ones are a little easier to find, although that would decrease the slope, not increase it. So yeah, so I'm not sure exactly what's going on. I'm really curious to see if people have other ideas too.
All right, the next question is, I'm sorry for pronunciation, at Denez. Could ice craters be a clue about how that region was formed or its tectonism?
I don't know a lot about that actually. I think I will say that the locations where the ice exposing craters are found line up really well with ice stability theory. So if you look at kind of like the atmospheric pressure and the water content of the atmosphere, it makes sense that there is shallow ice at these locations. But I don't know a lot about, you know, how it got there originally or how that region formed.
All right, and I think the final
Colin would be Colin Dundas would be a good person to ask that question of.
Yep. All right. Sorry for interrupting you. I think there's one question left, and that's from Clark Chapman. Is it thoroughly understood what makes the large, dark, or light-toned halos and ray patterns around these craters? Is it possible that some recent small impacts do not form such large spots and might therefore be missed?
Yeah, I'll say no, it's not thoroughly understood at all. You know, there's a number of different types of albedo patterns around here, right? So that's kind of what we try to separate out here. There's this kind of halo, there are rays, those are the pretty common ones that are allowing us to find them. But I mean, we don't necessarily know the specific mechanisms of the formation of those, and it's more than possible, it's almost certain that new craters are forming in other areas of Mars that we're not finding them, because there's no reason why they would only be forming in the high thermal inertia areas, right? So there's certainly craters forming over here, we just have not found them, and it's because they don't form these extended blast zones.
Okay, Michelle noted that you started a minute late, so you have another minute, but there are no more questions in the chat. But I actually have a very quick yes or no question. Have you searched all CTX temporal pairs, or not necessarily pairs?
I think that's a great question leading into the next talk, who I forgot to mention. I meant to mention this, we're working with a group that's doing some automated searches of CTX images to look for more of these, especially in the areas where, you know, we're not finding them. So I think that'll lead into the next talk.